All right, so we started from the ideal of, we started machine learning, building machine learning model. I think that was 2 weeks ago, and we talked about that machine learning is a way of supplying or allowing the machine or the algorithms to design rules from data without being explicitly programmed, design rules to predict a particular target without being explicitly programmed. And then we said there are two main types, 3 types, but 2 main types of machine learning, like supervised learning and unsupervised. The third one is reinforcement, but the 2 main types are supervised and unsupervised learning. And by supervised, we said that is when your data has the example of the output that you are interested in predicting. That's what makes it a supervised. And examples of that are regression problems and classification problems. We said the unsupervised are when the example of the output, the target, is not available in the data. An example is clustering. When you want to cluster, you want to group customers of a particular product, maybe based on how often they buy the product, or maybe based on their spending habits. So you want to know customers to focus on, to advertise more to pay more attention to, or you want to look at, maybe you want to build a model for a big supermarket. You want to give them a model in terms of to know which product to display more in an attractive section of their supermarket. So you build a product, a clustering to cluster, to group those products, maybe based on how fast they are being sold. So those ones, or maybe so those products that are being sold very far, you put them in a group, and that is the one you are displaying to customers as they are entering there. So that is an example of unsupervised. Okay, so but for supervised, we said we have regression and classification. We've looked at linear regression. So we said the goal of regression is to predict a numeric output. And we talked about linear regression, and we said when linear regression overfit because there are multiple variables, many features, there are 2 ways to regularize those models. That linear regression is using the ridge and lasso regression. And one thing, the only difference between ridge and lasso was that ridge makes use of L2 norm distance, and lasso makes use of L1 norm. And lasso normally forces the coefficient of the variables in your data to be exactly 0, thereby not making use of them in the model. Okay, and ridge forces them to be close to 0, not exactly 0, just reducing the impact of those variables in the model. All right, so, and then today we want to look at the classification aspect of supervised learning. So by classification, it's just a way of predicting categories of a target. For instance, if you want to build a model to predict whether an image is a cat or a dog, so there will be label for the cat, maybe 0, and 1 for the dog. So that means we're interested in predicting mainly the dog. So you want to show your model an image, and you want the model to predict that, oh, this is a cat, meaning predict 0, or predict 1 to represent dog. So that's what we call classification. And specifically, that is called binary classification because it has just 2 classes. There are situations where your target will have multiple classes. Like you want to predict whether a digit is 0, is 1, is 2, is 3, 4, 5, 6, 7, 8, 9. That's 10 classes. So you want to show your model a particular digit, and you want the model to predict whether it is either 0 or 1 or 2 or up to 9, any one of them. So that is multi-class classification. That's not binary. It's binary if it is just 2 classes. Multiple classes, that is multi-class classification. Okay, so but we've been focusing on binary, but I just want to let you know that you can have cases with multiple classes. All right, so logistic regression is mainly designed for binary classification. Although there are variants of logistic regression that can be used to tackle multi-class classification, like multinomial logistic regression, where we have all one versus rest or all versus one, things like that. But I will only focus on the type that is binary classification because that is the most common you will see out there. Okay, so logistic regression is still a linear model. Is a linear model used for classification problem. Okay, so even though it has regression, it is not used for a regression problem. Regression problem, remember, the goal is to predict numeric variable. But logistic regression, though it has a regression in its name, it is used for classification problem, not for regression problem. Is that clear to everyone? Okay, but it's a linear model. All right, so like I put here, is a statistical method for predicting binary classes. I've explained what binary classes are. Okay, it still have the same model, the same, because it's a linear model. So you still have a kind of equation very similar to that of linear regression. All the beta not beta one that you're seeing there, those are the coefficients. Those are the coefficients that the model is trying to learn. Okay, that's what the model is trying to come up with. Remember, the goal of the machine learning algorithm is to try to come up with the appropriate values of these coefficients, which in this case will represent by betas, okay, that will help predict the y. The x you are seeing there, that's the data we have. X1 is just one feature in the data. S2 is another feature. S3 can be another one. So, and it depends on how many variables you have. But those x's are the variables in the data. Those beta, they are not given. That's what the model is trying to come up with. So before the model come up with it, before you give data to the model, it is called algorithm. Oh, logistic regression algorithm. But after you supply data to the model and the model come up with some with appropriate coefficient for appropriate values for this beta, that is when it is called model. I mean, the algorithm come up with appropriate values for this beta using the variable, the x's. That is when the algorithm becomes model. That's the difference between algorithm and model. Algorithm is before you supply data to it. After you supply data to it and you try to come up with appropriate values for these betas, this coefficient, then it is called a model. That's when you can now use it to predict on new data. Is it clear to everyone? Is it?
Yes, sir. Yes, sir.
Okay. All right. So this is an example. So the X1, X2, X3, those are the variables in the data. So the theta 1, theta 2, theta 3 are the one representing the beta I showed you. So some people will use W, W is not the plus W1, W2, W3. Some people can use theta 1, theta 2, theta 3. It doesn't matter what they use. Those are the coefficients. And some people call them weights. Okay, it's the same thing. Coefficients, weights, that's the same thing. Okay, so the model is trying to come up with appropriate values of those. Even when you are regularizing, it is this weight, this coefficient that you are trying to regularize. Because if the coefficient is high, it will make the variable that has that coefficient to have high impact in the model. If the coefficient is small, it will make the variable that has that coefficient to have small impact in the model. So when you apply regularization, you're only trying to reduce the value of those coefficients, thereby reducing the impact of the variable in the model. That's all you are doing. And that's what machine learning is about, coming up with the appropriate values of W to reduce the error the model is making. That's what machine learning is about. So you can see, so you have three variables with the associated coefficient, and then you want to predict whether someone is happy or sad. This is an example of what we call emotion mining. You want to mine the emotion of people given the data. So based on maybe the statement the person is making, you say, oh, this person, you build a model to predict whether the person is happy or the person is sad. And you can even add a third category, neutral. An example of this is sentiment analysis, where you get, I mean, based on the data you want to predict, maybe like a product, a company is actually, they made a product and people are interacting with the product and people are giving feedback. This product is bad, this product is good, this product is bad. So based on their statement, you want to predict the sentiment, if it's positive or negative or neutral. So the positive, negative, neutral will be the classes. That means 3 classes. And if it's just positive, negative, that's 2 classes. Okay, so that's just, so you can use logistic regression. Logistic regression is used in many organizations that are using machine learning model. Okay, so it's very compulsory that at least you know logistic regression. Yes. Okay, any question? Is it clear? All right. Okay, so applications of logistic regression, like I gave, so this is, one is spam detection. That is, that's like Yahoo, they do that, Google, Gmail. There is a spam detection model that is working underneath your, your email that you don't know. You will see that some email has been classified as spam. If you check your spam folder, you will see so many emails. There is a model running underneath such that there is a pattern in the data based on, so maybe based on numbers, if the numbers there are too many or the emojis or things like that, it can detect that email as being spam. It will classify. So it's not perfect. Sometimes they wrongly classify email as being spam or not. Have you received email from some, I don't know if you have tried to apply it to some people, they will tell you that please also check your spam folder in case you didn't hear from them. That I don't know if you have ever received such email, yeah, that's because that's because it's not perfect. So sometimes it can wrongly classify a correct email as being a spam. Okay, but most of the times, at least the accuracy is high, the performance is high, like over 90%. So meaning that majority of the emails classified as being spam are very correct. And that's why we use another metric called confusion matrix, because that is very well explanatory. And I said I want to see that too in your project. Okay, another one is diabetes prediction. You want to predict whether a patient is diabetic or not, maybe based on the weight, the features in the data like the weight, the body mass index, that's BMI, the sugar level, or things like that. So based on those features, you want to build a model to predict whether a patient is diabetic or not. Or customer churn. Customer churn mean like, you want to build a model to predict whether a customer will leave a particular product or will stop patronizing a particular organization and leave for his competitor. Like in Nigeria, I know there are different variants of people who made detergents. There are different variants of organizations. So maybe instead of buying, I can't remember most of those things, most of those names again. Maybe instead of buying one, you want to go for the other one, so you want to predict whether a customer will stop, buying product from this organization based on the other. So that would depend on the data you have, or whether or not a user will click on a given advertisement link. So there are so many times you receive emails and you don't even know how these people are sending emails to, and they're advertising something. So you can build a model. If you have so much of those data, we can build a model to see whether or not the user will click on a given advertisement. So there are several applications, okay, real life application that thrives on data. All right, so examples like we have just said, whether you want to build, this one is called fraud detection. You want to build a model to predict whether credit card occurs or not. Another part of it is that maybe you want to make it real time, and that could be very challenging, but there are platforms framework that organizations are using, operating those models in real time, or predicting whether a patient has cancer or not. So here I just show an example of linear regression and logistic. So look at the problem with linear, why we cannot use linear regression for categorical data. Remember, the binary classes will either have 0 or 1. So the data will only be at that straight line where y is equal to 0 or where y equals to 1. If you try linear regression, look at the line. It's just going to put a straight line through it. And that will be, the error will be so much. Okay? But logistic regression is a curve. It tries to predict probabilities. So this is how it's been done. It sets a threshold, maybe like 0.5. So instead of saying 0 or 1, if the prediction is below 0, it's going to classify those ones as 0. And if its prediction is below 0.5, it's going to classify them as 0. And if the prediction is below, the prediction is above 0.5, you can classify them as 1. You can increase the threshold, maybe to like 0.8, so that everything below 0.8 will be classified as 0. Everything above 0.8 will be classified as 1. So it depends. So logistic regression is mainly like a probability. So it's predicting probability. You can also predict classes and you can predict probability. So there is that option for you in logistic regression. And we can see them when we want to implement them in scikit-learn. All right. So the advantages is that it does not require high computational power. It's easy to implement and easily interpretable. And it provides a probability score. That's what I just said for observations. Instead of just the classes, you can predict the level of uncertainty, how certain that what you are predicting is going to be in class 1. That is it. So that's what the logistic regression is doing. That's that measure of that probability. Okay? All right. So the disadvantage is that it's vulnerable to overfitting. It performs poorly on nonlinear data because it's still a linear model. So it's going to perform very well, poorly on nonlinear data. And if the features are very large, it may not be able to handle that. So it may actually be poor. Okay? Any question before I move to implementation? Any question? Is this clear? All right. So let's see how to do this in so everything I've explained is also in the notes, and you have the access to the notes. Okay, so but one other thing I just wanted to add is also idea of regularization. Okay, so can anyone summarize what regularization is? What do you mean by regularization? Huh? Hello?
Hello, sir.
Yeah, go ahead.
Regularization it's like a method to reduce overfitting, but like reducing the weight of each data, because like the higher the values, the more they have effect on the regularization is more like a way of reducing the, the coefficients of each
variables. Okay. Yeah, that's fine. Thanks, Samson. So that's it. It's actually a process of restricting the weight or the parameters of an algorithm to a specific value. It could be 0, like lasso, such that it prevents our model from overfitting. So you are exactly right. Okay, for logistic regression, so for logistic regression, there is a particular parameter in that model that does the regularization, and that parameter is C. I will show you. That parameter is called C. Now, higher values of C correspond to less regularization. So this is contradicting to the way we did lasso and ridge. For lasso and ridge, there is a parameter called alpha, if you remember, that does the regularization. And higher values of alpha means more regularization for those lasso and ridge. However, in logistic regression, it's like inverse. The parameter is C, and when you, the smaller the values of C, the more the regularization you are applying. The higher the value of C, the lesser the regularization you are applying on the model. So it's like inverse of what you saw in the alpha for lasso. Is it clear? All right. So let's try a built-in data this time around. I'm not going to use our own any data. I want to use data that comes with scikit-learn. Okay, so there are some data there and you can use them for experiments. Okay, so I'm going to use the cancer. It's a real world data actually, but they've put it inside scikit-learn. So it's a breast cancer data. Okay, and it's inside scikit-learn data set. So that's why I wrote from scikit-learn data set import. It's called load breast cancer. Okay, so here I want to create an instance of it and call it cancer. So if you want to know the data there, just check the keys or the info. Check the keys of this data. So you can see. So this is how all the data that comes with scikit-learn has been sectioned. So they've removed the features, the variables for you. They've put the variable names in another, like these are the variable names, the feature names. It contains the variable name. The data itself is here, and they've removed the target variable from it. Okay, I've already shown you how to get all of this from your own data, and I mean, did that in the assignment. So if you have done it, you should know, and we've been doing that too, where we select our features and target. But here they've created the data for us. That's the feature. So these are the features, and this is the target. These are the names of the features. So all these data, they are in NumPy array. And if you remember, I showed you how to convert your data frame to a NumPy array. Do you remember? What do you need to do to convert data frame to NumPy array? Anybody want to remind me? There's something you just put when you select the features at the end.
Dot value.
Dot values, thank you. So
Dot values.
Yeah, so that's it. So they have converted it already. If we check, let's experiment the data. So if you do cancer.data, I'm only picking this guy, cancer.data, just call it dot on it. I call it cancer because I name it cancer here. .data, I'm only selecting this particular one. So if you do that, see, you can see that it's a NumPy array. They have selected it for you. And if you check the target, see, there is 0, 1, because there are two classes. Either the patient has cancer or not. And if you want to check the target names, see, so it's whether the patient is malignant, that is harmful, or is, benign, that means it can still be treated. Okay, so that is it. So like a cancerous cancer and the one that is not cancer, that it can be treated. So that's benign. So this is like the 0 or 1. This is like the 1. Okay, and then you can also check the feature names, the variable name. There are so many feature names there. So there are many. Okay, and then you can, if you want to convert this data back to data frame, you can actually do that. So I will just convert it, but I won't use it. I will use the one they've already segmented. But in case you are wondering, you want to see them in a table, I can do that. Let's call cancer DF. Okay, so let's import. I don't know if I've imported pandas before. So let's just import pandas as PD. Import pandas as PD. Okay, so from the PD, we call on the data frame method, and then our data. So the data should be our cancer data, and the columns should be the cancer feature names. That's all. Let's check if this is correct. df.add. Okay, yeah. So that's it. So we've converted the data to data frame. So this was what it was before. So they only selected the features and the target and put them in the package. So that's just it. So these are the features. You can see it has 30 columns, 30 variables. The target is not there because they've already separated it. So and you can check the shape of the data to know how many rows. We already know how many columns. It's 30 columns. So these are the variable names, and then you can check. But one great thing is that all the data inside the scikit-learn has no missing values. If you want to confirm, you can check cancer df.is_na.sum. So you see that no missing value, you can see. So there's no missing values there. Okay. And then what else? So you can exploit, you can do you can call the describe method, do all of those things there, but that's not my goal here. I leave that one for you because you're going to do that in your project. Okay, remember you can check the correlation. All right. So, so one thing you want to do now, we want to split the data. They've said I will use the one they've selected for me, the data and the target. Okay, so I want to split them. So we import from scikit-learn model selection. We've already seen this before. We import the train test split. So let's have the X train. Let's have the S test. Let's have the Y train. And let's have the Y test. So I'm going to call on the train test split, and I will pass in the cancer data to be split into X-train and X-test, and cancer the target to be split into Y-train and Y-test. I want to use the default 75 and 25. Remember, if you want to check the shape to know how many rows you can do that. Okay, so it's just 569, right? So I will just use the default of 7525. So let me set the seed, random seed. I'm using 0. That's all. Okay, then I told you that it's a good idea to always scale your data. So we've used min max before, like getting the minimum and dividing by the difference between the minimum and the maximum. Okay, but let me try another scalar called standard scalar. If you remember, I explained that the standard scalar will scale all the variables in the data to have a mean of 0 and a standard deviation of 1. That's all. The min max will scale all the variables in the data to be within a range of 0 and 1. So all the values all the variables will now lie between 0 and 1. That's what min max is doing. Okay, but standard scalar will scale them to have a mean of 0 and standard deviation of 1. Okay, so let's name this. Remember, here I'm not using function. Remember, I've taught you how to put all of this process in a function. So instead of doing it this one by one, you can start by doing this one by one, but the one you will submit in your project, use functions. I've taught you functions, that's why I'm not doing that again. I've used that in 2 classes. And I gave you assignment, and at least from the one person that submitted, I saw that you guys, I agree that I'll conclude that you guys are good with that. So that's what I'm doing in one by one. You can start one by one, but put everything together in a function. Okay, so X-train, STD, let's use that for the scaled one. Okay, so but we have to create an instance of the scalar. Let's call that scalar and call the standard scalar. Okay, so after creating an instance, we use that to fit and transform the X train. And for the X test, so are we going to call fit transform on the X test or just transform?
Just fit, sir.
Why just transform? Why are we just calling transform? Why not fit transform on the test set?
You
Yes,
explained that if you use fit transform again, then it's going to more like do another type of fit transform on the X test. But if you are just using transform instead, it's more like it's continuing the same format you used for the previous one for the X test.
that's right. Thank you. So when you call fit and transform on the training, the fit is what we bring we bring all the variables to a mean of 0 and 1, but you won't see it. But when you call transform, the effect takes place. If you call it again on the test set, it's going to do exactly the same thing, and then the data distribution will not be the same, and that will lead to a very poor model. But do it on the training and use the result of the training to transform the test. That's all. That's why we are only calling transform on the test set. Okay, so we run this and then we are good to go to build the model. So to build the model, since it's a linear model, so from scikit-learn linear model, we import logistic regression. So we create an instance of it. Let's call it logreg. Okay, you can give it a name that you want. I will use default parameter for now. That's the default without regularization. Okay, then we can fit the model, logreg.fit, and then we fit it on the scaled, the training data, and the Y train. And then we also want to check accuracy on both the training and the testing. Okay, so we have the prints, and then let's call this training accuracy. So let's make it to 4 decimal place, and then call .format and pass in logreg.score. .score is what will calculate the accuracy, and put in the X train XTD, that's the scaled, and the Y train. So let me just copy this and change it for the test. So I believe this code you should be familiar with that now, since we've been doing this test accuracy. So, and then we change this one also to test, and then we change this to Y test. Okay, so see, that's a good so look at it. So on the training, even though the data was small, we have like 99%, and on the test we have approximately 96. So this means 96% of the time this model will correctly predict. Remember, you are only interpreting the testing, not the training. 96% of the time this model will predict that correctly predict that the patient has cancer or not. So it will fail like 4%, but that 4% can be huge. You know, this is person's life. You want to, a patient come and then if the person doesn't have cancer, you predict that he has cancer. I mean, that one is still good, at least it can, but that one can even kill the person. What if the person go and commit suicide? But the one that is worse is that the person has, and the model predict that the person does not have cancer. And the person just find himself that is dying daily, just feeling, and before he knows, it becomes like beyond repair. So it's still costly, that 4%. So you don't stop there. You don't say, oh, 96%, that's great. No. You want, as a data scientist, you want to try as much as possible to see if you can get better results, better performance. However, don't just stop at accuracy. One thing in your model, the project I gave you, let me quickly give you an expo. The 2 projects you are working on, most of the data, in those 2 classes in the target, one class has more data than the other. If you are using accuracy alone, the model will be very high, the performance will be high, but it doesn't mean that the model is actually a good model, because the model might just be predicting the most occurring class, which is the negative class. It's just predicting it because that's what it sees more. it doesn't mean that the model has actually learned. So that is a problem I did not teach about. It's called class imbalance or data imbalance data problem. You have you have to search the internet on how to resolve imbalanced data. Build the model while it is in balance and try. If you can do this will be great, because then you will be very eager, like you will be able to share what you have done. It's your work, it's not me, it's not for me. Try. There is a way to resolve it, and I can give you in. Okay, if you search online how to resolve imbalanced data, there's just a package you will install. It's just 2 lines. It will help you balance the data. Okay, so once you build the model with imbalanced data, try as much as possible, if you can, to balance the data and rebuild the model, and you will see the performance, and the performance will be high. Like the performance will be reliable even when you use precision and recall. If you use accuracy for imbalanced data, it will be high, but precision and recall will be low. So that shows your model is not doing well. But if you balance the data, accuracy will still be consistent, and you will see that the precision and recall will be high. And that's why in the industry today, they use precision and recall, which I will talk about, to judge the performance of a model. So those 2 data you are working with your project, anyone you want to choose, they are imbalanced. So I just give you that hint. Okay? Are you still there, or you are scared now? Like, I'm not even going to do this project. Remember, it's your work, and you can share it in any interview. If you are, it's your work, and you can put it in your GitHub. It's your work, is not for me. Okay? All right. So now we want to see if this model is still overfit, because it's 99% on the training and about 96 on the testing. So remember, one way is that we can regularize the model. And I told you that there is a regularization parameter in logistic regression called C. Watch, let me push Shift Tab and read it. So there are 2 ways you can regularize this model. You can use the penalty, which is the norm, the L. So remember when I talked about Ridge and Lasso, I said the Ridge uses L2 norm, Lasso uses L1. So by default, logistic regression uses that L2 norm. It's a distance approach that also helps regularize the model. But the C, the main regularization parameter, is this. So you can use any of these 2, and you can use both. We can switch the penalty to L1, okay? And we can also adjust these values of C. This C is the regularization parameter. You can read about it. So if you can see the L2 and L1 now. So if you are reading, if you want to look at the C, say inverse of regularization strength, it must be a positive float. Okay, so is the main parameter. Remember, smaller values means more regularization. So let's try to do that, and that's what I'm doing here. Since the default is 1, I want to try smaller values and see. Just the idea we did before, like running a for loop, and picking the values one by one. We did this for Lasso and Ridge using the alpha. So I just set these values. They are arbitrary, meaning you can set your own. Okay, I have a place to store the training accuracy and the testing. And then I loop over it that for C in the values of C, create an instance of the logistic regression using the value of C that you pick. The first time is going to pick this and fit it on the scaled. So that would be STD. Okay, and then train, and then check the accuracy. Check the accuracy, yes, on the training, the scaled data on the training, and the test. So we're using log reg, not log reg 1. Okay, so I just want to visualize. You can see, so I save it as a new model here. I mean, it doesn't matter anyway, but I just change it on a new model just to differentiate it from the original one. Okay, so that's what I was saying, that let your original, the regularized name should be different from the original. Does anybody want to ask a question? And then we can plot it. So we plot the values of C on the x-axis and the training accuracy on the y-axis for both training and test. And then we show the legend, and then this is it. So it's going to take, so you can see that the model overfit almost all the time. So it's just that it comes up a little bit when the values of C is like 0.5. So the idea of visualizing is to pick that value and rebuild the model. So rebuilding it, you can say I name it logreg1, not the original logreg. So now I'm using the C value of 0.5 based on my visualization. At least that is still better than when it's 1. Look at when it is 1, see the accuracy is about 95. So, but when it's 0.5 is still higher. So that's the value I'm now using. And I'm rebuilding the model, okay? So, and I'm checking the accuracy again. I don't know if what I'm doing makes sense to you guys. Does it? So yes, you can see now. All right, so now when we check the training accuracy, it reduces from 99 to 98.8, and the test accuracy increases from 95.8 to 97.9. You can see that is still better, even though it's still not the best. It's still far better. At least now we've reduced the error, the 4.2% to be 2.1%. That's about 50% improvement. That's great. So, but you still want to see if you can do better, okay? We've already normalized, so I'm going to skip all of this. So, but you still want to see if you can do better. So, and the only thing you can try again is to see if we can vary the regularization parameter. You know, like the penalty, like to see if we can change this to L1. However, there's a condition. If we change the penalty to L1, so you have to read the documentation. It said it can support L1, L2, elastic net or none. Default is L2. So now watch what it says. It said LBGF solvers. So there is a solver parameter that supports only L2. And so if you want to use L1, you have to change the solver. For instance, look at it. It said L1 penalty with Saga solver. So let's check the solver parameter. Otherwise, we'll get 0. See, the default is LBGS. And it says that LBGS by default only supports L2. So if we change the penalty to L1, then we have to change the solver. We have to change these solvers to make one of these. So we can change it to linear if we change the penalty. So that's what I would do. Yes, I will change the penalty. I will change the penalty. So we can even try this as a new model, you know, like logreg 2. So every time you try something, you can save that as a different model to show. So instead of changing this, let me just copy and try it in a different cell. So show what you have done. So instead of changing it in one place, okay, so we can change the penalty to be L1. So I have to change the solver to linear, if I'm correct. And then we'll try it. Let's see if, oh, do you see what I'm showing?
Yes, sir.
Okay, great. So you can, this is what data scientists do. It's not like you just take data, you build model and you are done. No, you are going to try different approach. And that's why I said you can explore other models too. Okay, you don't have to know how deep they are working. I mean, in the future to work, you can read about them, but at least you can try them out. So look at it, just changing the penalty from L2 to L1. Look at what happened. Even at 0.0 One, the model, the training accuracy and the test appears to be the same. So we will rebuild the model using like that value of 0.1 or 0.15. So that's what we'll do. So let me copy this, but I will name it logreg2 now. Okay. So I will name it logreg2 and change this to 0.1. Let's see. So logreg2, and see. No, so I think it's 0.15. Let's see if I'm correct. Am I getting this wrong?
I think the penalty, you have to include the penalty and all those things.
Oh, that's right. Sorry, that's a good catch. That's a good catch. So let's see. Okay. So, but let me see 0.1 first. I think it's 0.1. Yes, it's 0.1. So look at it now. So the training accuracy, this is 97.89, and here is 97.9. So it's even better. This, it was exactly this, but now it reduces this now. It reduces the training accuracy. So the model no longer overfit here. So this logreg2 is reliable. The reason overfitting is a problem is that if you build a model that overfits, and you give it to your organization and they put it into production and they start using it to make prediction on new data, the model will perform poorly and they may lose a lot of money. So you want to give them a reliable model. So this one is reliable because it does not overfit. So this is a good model to handle. So you can see all the different things I tried. That's what I want to see in your project. You may, in presentation, you may not show the details. You can just show like the different plots and label it like, oh, this is a plot without regularization, or with regularization, with just values of C ranging between this, and the penalty is L2, and this one is with different penalty L1 and the solver. You just show the visualization and then show the performance, you know, things like that. Hello, Pandas. Do you have a question? If you don't have a question, please be muted. So that's what I want to see. I mean, you have to show me the code in the Google Colab, but in your in what you are submitting online on Canvas, you have to show the code. But in presentation, the plot is enough. The plot is okay. I don't know if you are getting what I'm saying. Are you?
Yes, sir.
Yeah, I know it's getting complex, but that is it. That is, if is all with everything I'm doing here, we've covered it before, and that's the standard. And I want to give you the standard. I don't just want to give you a shallow something in academic. No, I'm giving you from the industry perspective. Okay, so, and that's it. When you want to do a project, your project, it should be standard. You should try as much as possible to put in the best, because you can share it with potential employers. Okay, so that's it. So we've been able to pick the model from an overfitting model to a model that generalizes well. So this model, we can say this model generalizes well. So I will only finalize everything by introducing you to the concept of other performance metric like confusion matrix, because I want you to use it, recall, and precision, and maybe with F1 score. So these are the reason we don't stay with accuracy. I've told you, if the data is imbalanced, the model may just be predicting the positive class or the negative class, the class that occurs most. It may not, that model will not generalize well. Okay, even though it does not overfit, it's only predicting the negative, the class that occur most. So you want to try other performance metrics like recall, precision, and F1. If the model is consistent also on those other metrics, then it's a good model. If it has high accuracy but low precision and recall, then the model is not reliable. Okay, so, all right. So
Yeah.
do you have a question?
Please, can you say that performance matrix again, like slowly?
I'm going to talk about them. They are here. Recall and precision. Okay, I'm going to talk about them. I'm just saying that if your model performs very well using an accuracy metric that we have been using, and it gives, and if I'm trying other metrics like precision and recall with F1 score, if the model gives low precision, low recall, low F1, but high accuracy, that's not a good model, because it shows that the model, and that's what happens for imbalanced data, is only predicting the class that will occur most. So you want a model that has good accuracy, good precision, good recall, and eventually good F1 score. That's all I'm saying. Okay? All right. So now this is an idea of confusion matrix. So it's a 2x2 table. Don't mind the name. Okay? They call it confusion matrix. So usually the actual target is on the is this horizontal. So we assume that we've coded the positive class to be 1, the negative class to be 0. Like cancer, someone has cancer. Maybe that's the positive class. That's the one you coded 1. Someone does not have cancer. That's the one you coded 0. This is what the model is predicting. That's what you see on the vertical, 1 and 0. So this particular part where we call true positive, it means in the data, we have that a patient is positive, and then the model is also predicting that the person is positive. Like a patient is pregnant, the model is predicting that the person is pregnant. So the model is performing well there. That's a good prediction, right? That's why we call it true positive. A patient has cancer, the model predicts that the person has cancer. That's true positive. So that model is that's good. The other one at the far right corner is the true negative, meaning the patient is not pregnant and the model is predicting that the patient is not pregnant. The patient doesn't have cancer and is predicting that the patient doesn't have cancer. The person is not a criminal, is innocent, and the model is predicting that the person is not a criminal, that the person is innocent. That's true negative. It's negative because it's the other class, like not negative, like not criminal, not pregnant, doesn't have cancer. So it's the other class. So that's true negative. Where the model is making mistake are these false positive and false negative. False positive means the model is wrongly classifying it as positive. Like a patient who doesn't have cancer, the model is wrongly classifying the patient as having cancer. That's false positive. So if person is criminal is the positive in our class, in our data, and the model is wrongly classifying an innocent person as a criminal, then that's false positive. Is it making sense?
Yes, sir.
So that's error. Another one is the false negative, meaning the person is pregnant and the model is saying you are not pregnant. The person has cancer. The model is saying you don't have cancer. Don't have cancer, remember that's the negative class. So the model is wrongly classifying a positive instance as a negative instance, saying you are a criminal, you are not, like the person is a criminal, that's the positive class, and is wrongly classifying the person as not being a criminal, as innocent. So things like that. So those are the two places the model is making mistakes. So if you want to be able to explain the performance of your model, is a good idea to try out to calculate confusion matrix on your model so that you can explain. You can explain the table that, oh, out of this sample, our model is classifying this as being positive, this has been, you can explain it in terms using the terminologies of the data, not just accuracy or recall. So you also want to compute the confusion matrix. And I want you to do that in the project too. Before I talk on the precision and recall, let me quickly show you how to do confusion matrix. So we can import it from scikit-learn. Everything is in scikit-learn. From scikit-learn metrics, because they are metrics. Import confusion matrix. Let me also import classification reports. Okay, so let's create an instance of it. Let's make a prediction, because remember in the table we have predicted where our model is making prediction. So let's use the best model that we did here, which is the logreg2, to make prediction on the test set. Okay, I know today I'm a little bit fast. Yeah. But I assume that you are following. So logreg2, you can see all the three models we have built. So let's use the logreg2 to make prediction. So you can see, this was what I was explaining. You have option of predicting the classes. You have option of predicting probability. The predicting probability is the predict prober. I won't go into details on what you can use it for, but you can explore what we call ROC curve or ROC AUC score. ROC stands for Receiver Operating Characteristic Curve. AUC stands for Area Under the Curve. So that's another metrics. If you want to use that, then, and you're using logistic regression, then you'll be predicting probabilities. But I won't talk about that. At least, so let me just use the predict to predict the classes. So I'll pass in the X test that we scaled. So this will give us the prediction. Now, I want to use this prediction with the true target, the actual value, the true target, to get the true positive, false positive, and all of that. We have the true target in the data as the Y test. So now let's call conf, let's save it in that variable and call our confusion matrix. So confusion matrix, the first thing you pass is your true target, and the second one is your prediction that we just made. That's all. We can also do that for the classification report. The classification report is very similar to the confusion matrix, just that it gives us a comprehensive explanation of the resulting confusion matrix. So let's call that CLS reports. Are you guys following? The same parameter, Y test and Y prediction. Are you following, or I've lost you?
Yeah.
Okay. Okay, so let's print it out. So let's call this confusion matrix. Awele, are you there?
I'm here.
Okay. All right, so let's put this in a new line because it's a table. So let's just put \n. \n means in a new line, okay? So let's do dot format and pass in the confusion matrix that we did. So let's print this and then we can show the classification report in the next line. Now, so the way this works is that it inverts it. This is the true positive. It inverts, confusion matrix normally inverts the class, okay? So this is the true positive, this is the true negative, okay? So this is the false positive, this is the false negative. So you can see that the accuracy we got, because we've worked on the model very well, this model makes less mistakes. See, it wrongly classified two people two people that has cancer that they do not have. But analytically can find one person that does not have cancer as having cancer. We can try it on the first one, on the log reg or log reg 1. We can try that and see. Let's do that exercise. Before this, let me create a cell and just do that for log reg. Okay, so let's make this Y predict. Let me call it original, ORG. And then the confusion matrix, let's call it confusion matrix 1, class report 1. Okay, so this is ORG. Confusion matrix 1. Okay, so let's try it on the first one. Now, you can see the difference that it makes more mistakes. 3, 3. And then the one we correctly classify, the true positive and the true negative, they're a little bit lesser. So you can see that the better your model, the more, so this is saying, so you can explain this. So if you do the confusion matrix, explain it that, oh, our model is saying, is predicting 2 patients, you know, in the context of the one you are working with. So our model is predicting 2 patients who do not have cancer. This is false negative. 2 patients who have cancer as not having cancer, as not having breast cancer. And it's predicting 1 patient who does not have who does not have cancer as having cancer. So you can explain the model. You can see, so the confusion matrix helps you to explain your model. This is the false negative, this is the false positive. Is the explanation clear to everybody? Is it? Hello?
Yes, sir.
All right. So we can also, okay, go ahead. You want to ask a question? Okay. So you can, you can also check in the classification report. We'll just, do the same idea. We don't need to, we've already done the classification report for this, so I can just classification report. Classification reports. So that's CLS reports. So this gives us, this will give us precision and recall and F1 score, which I will explain now for that. And we can also manually get this. So we are interested in the 1 class. This is the one we're interested in. This is the negative class. This is the positive class. So classification report will show you the precision, recall, and the F1 score on the positive class. You can see it even gives you the final accuracy. You can see it's 97.9. So it's run this up to 98%. So this model has precision of 98, recall of 99, and F1 score of 98, which is, so this is consistent with the accuracy. So this is a good model. If the model has high accuracy but low precision, low recall, and F1 score, that would have been a poor model. How did you calculate the recall? It's very easy. It's calculated from the precision. So F1 score. So F1 score is just 2 times precision times recall divided by precision plus recall. So that's what the model used to calculate the F1 score. It's just this formula. 2 multiplied by the precision and the recall divided by the addition of the precision and the recall. If you want to jot it down, you can put it down. Otherwise, I can rub it up. So that's just it. That's how I calculate. So that means before we calculate, if you want to manually calculate precision, F1 score, you have to calculate precision and recall. There is a function to do that in the scikit-learn metrics, precision score, accuracy score, and F1. I can show you, but it's going to be the same thing. Okay. All right. So let me just explain what they mean. So let me start with precision. Precision just means that out of all the positive class that our model predicts, how many are truly positive? Out of, see, the denominator is true positive plus false positive. Let's check this. So true positive plus false positive. So this is where our model is predicting positive class, the one. So out of all these positive predictions that the model makes, how many are truly positive? That's why it's doing true positive divided by true positive plus false positive. So that's the positive prediction the model is making. Out of the positive prediction, how many are truly positive? That's what precision is calculating. Is precision clear?
Yes, sir.
Hello?
Yes, sir.
Yes, sir.
So that's what I put here. Out of all the positive class we have predicted correctly, how many are actually positive? Now, recall is doing, out of all the positive that we have in the data, out of all the positive class in the data, not in the prediction, out of all the positive classes in the data, how many did the model predict as being positive? That's recall. Out of all the positive classes in the data that we have, how many did the model predicted correctly? That's what it's doing. So if you see true positive plus false negative, is this column. You can see this one, that's the actual value. So this one is the positive in the data, the positive classes in the data. And that's the where we have the true positive and false negative. How many is the model, did the model predicted correctly? So precision is out of all the positive predictions, how many are truly positive? Recall is out of all the positive classes in the data, how many did our model predicted correctly? So that's why I put out of all the positive classes, how much we predicted correctly. So it should be as high as possible. So, and in this case, we got 99, which is good. So that means 99% of all the positive classes were predicted correctly. Well, so you can explain it from your understanding of what I've just explained. If you want to get them on your own, from scikit-learn metrics, we can also get precision score and recall score, even F1 score. You can get that. And it's just the same way. It's the same way you calculated confusion matrix, the same way you do that. So we can get precision score to be precision score. Just pass in the Y test and your Y prediction. The same thing for the recall and the F1. So let's change this to recall. And this one to be F1. Okay, so let's check. Let's check the precision. See, 97.8, which is approximately 98. Let's check recall. So it's giving you on the positive class. See, 98.88, which is approximately 99. And then the F1 score, 98.3, which is approximately 98. So if you want to get them without like, but if you use classification report, it's going to give you for both the 0 class and the 1 class. But if you want to get it on your own, on the positive class, then you can just use this idea. Import it from the scikit-learn metrics, import them just the way you run the confusion matrix is the same way you run them, and then you can print them or put them in a table. All right, so by this, I've come to the end of the teaching. Any question? I know it's a lot today to take in, and I thought for close to 1.5 hours. Any question? Please ask questions.
Sir, can you run us through the assignment again? How you want?
The project?
Yes, the project.
Okay, so let me pause the recording.